So let's say I want to fit a machine learning model, right?
Yeah.
And basically, the task is that I have some data. I have a lot of data. I have some arbitrary
Yeah.
data, right? So for, let's say for every x, I have y. Okay. And let's say I have a bunch of data, right?
hmm
Let's say these points, these dots are all my data.
Yeah.
And now I want to say, well, I see I have a bunch of data, and I wonder what would my result be if I have a dot over here, right?
Yeah.
But I don't know how to get that.
Right.
Well, one method you can do is simply draw a line that somewhat represent my data set
hmm
so that I can go to this point on this function. Let's say this is just linear. I can go to this function and use this as a formula to find the y value of this arbitrary point, wherever this point may be.
Yeah.
Right? We won't deal with bias yet. I mean, bias is just an extra term. So let's say the m is like describes our polynomial here, right?
Yeah.
It's just linears. And whatever m is will determine where my slope is. M is my slope. So now, does this make sense? The task that we're trying to
Yeah.
do here.
Yeah. I get it. Yeah.
So now you want to say, okay, well, I want to find this m, right? And the way I will find this m is not very clear off the bat, because like right now looking at this graph right here, do you know
Yeah.
the value of m?
No.
You wouldn't, right? It's really
No.
hard to tell, like what m would you choose, and then how would you do it so that it most accurately describes all of my data points, and may have
Right.
like thousands, million points of data. So therefore, what I can do is define a loss function. Let's say my loss function is MSE. Do you remember what MSE is?
I don't. I'm sorry.
Did he go? What loss function has he gone through in class?
Dude, I could not tell you. That's kind of why I'm here with you, man.
Okay, that's good. That's fine.
Yeah.
It's called mean squared error, MSE. Remember, mean squared error is for regression, and then cross entropy, which was what we did yesterday, right? Cross entropy.
Yeah.
Does that ring a bell?
Kind of. I heard him mention it.
Yeah, so cross. Okay, yeah. I fear this is what's been going on. It's like you guys hear the word, but like you don't really know what it is, which I
Yeah.
get it. He's like not really explaining it. Like I went to class yesterday, right? And then he just
Yeah.
kind of squibbles everything on the board as if they make sense.
I know, man. That's what I'm saying. I can't get it, man.
Yeah, which is
Yeah.
like, all right, guy, I get it. Like you're good at math. Anyway.
Yeah, exactly.
So mean squared error basically is the error here, right? So y hat is the predictive value. So let's say y hat is like this guy. I have mx, and my MSE will calculate the difference between my y hat and then the y
Yeah.
over here. Square it, and then add every single do that for every single point and add that together.
Yeah.
Does that make sense?
Yeah. I mean, I get kind of. Yeah.
So okay, let me draw some of this, some of the, like, this difference here, right? The y hat minus y.
Yeah.
So I just means for each point, right?
Right.
We have n data points. We have this n. We have n data points. We want to draw the difference. So my difference between the real value and the predicted value will be like the distances here.
Yeah.
Does that make sense?
Yeah.
Because the black dots are the real value, right? And then the
Right. Yeah.
red is like what falls on the polynomial, on the linear, is the difference. So you see how we square these? Each one of these, we squared these blue, the length of the blue, and then we
Yeah.
add them together.
Okay.
So far away. You see how like this point, for example, is very far away.
Yeah.
You square it, so that's gonna be a very big number,
Right.
right? So
Yeah.
in this case, my loss value will be very high. However, if this is very close to the curve, then I have a
I see.
really low loss value.
Yeah.
Right, so that describes how much is my loss, how far away am I from my real
Oh,
data
okay.
here.
Yeah.
That's what the loss function does. All right, so then what we're going to do is, matter of fact, take the derivative of L. Have you taken any math classes yet?
Yeah. I've gone through Calc 2, so I know the derivative and
Okay, just Calc 2?
yeah, just Calc 2, man.
Okay, that's fine. So what I am going to do is I'm gonna erase this temporarily, and what is y? Like how can I model y hat?
Is y hat the derivative of y?
No, y is the real value. Y hat is the predict value,
Okay.
right? And how do I
Yeah.
predict each value based on x?
You have to multiply it by m.
Exactly, right?
Yeah.
And remember, m is my weight. M is what I'm training here.
Yeah.
I want to get
see.
a m value that will fit, that will predict the good y value, right? So
Yeah.
exactly, yes. So this is my formula. This is my m. You can see that as my neural network. Right now, we're just doing one
Yeah.
neuron, which is fine, which is great, right? This is what we're doing here. So let's then take the derivative of L in respect to m, because we're trying to update m. Does that make sense?
Yeah, kind of.
So yeah, so okay, let's think back to derivative, right? So let's say you have velocity. Do you know what velocity is? Like in
Yeah.
terms of derivative?
Yeah, I mean it's like speed over time.
Yeah, exactly. So basically you can take, let's say you can take displacement over time and then take the derivative of the displacement. Now you get velocity, because that's what
Yeah.
it is, right? That's
Yeah.
speed is just the rate of change
Right.
of time.
Yeah.
Exactly. So same
Yeah.
here, same concept here. I'm trying to take the derivative of L in respect to m. So I'm trying to get the rate of change of that. I'll get to that why we want the derivative in a minute.
Yeah.
So basically, how would I do this, right?
Well, you just take the
N is
derivative.
just a constant because n is the amount of it. I take the derivative of this whole thing. Now I get 2 times like the whole
MX.
something. I won't write it all out, but like,
Okay. Yeah. I
right?
got you.
So you put the 2 in front, right? And then like
Yeah.
2 minus 1 here, so to the only to the first power, which is fine. But then remember,
Right, chain rule.
chain
I
rule,
gotcha.
right?
Yeah.
So chain rule, it was just gonna take the derivative of this in respect to m. So I just left with x. That's gonna be my loss. The derivative of my loss in respect to m.
Yeah.
Now, why is that important? Let's say I have another graph here. This models L when m. I assume that there is a curve of L in respect to m where there is a lowest point, where my loss is the lowest. That's the curve I want. That's the m I want to fit this curve, right?
Oh, I see.
feed
So
this
you're
data.
trying to find when the derivative is 0?
Kind of. But like you can do that, but then that doesn't really work well that way, because
Yeah, no, I get it. 'Cause it could also be like the peak.
it's just like,
Okay.
first of all, that may be local. minima, right?
Yeah.
Second of all, there's a lot, especially when you deal with like high dimensional data. So what you want to do instead actually is that you want to find, let's say my loss is first when I initialize this very high, because I just initialized the random line, right? Let's say I initialize the random line is this. I have a really high loss here, right? I don't like this loss. This is too high. This doesn't describe any of these points here at all. So what I do is I take the gradients. This is called gradient descent. Do you remember gradient descent?
Yeah, I remember him mentioning it.
Yeah. So this is called gradient descent. And what gradient descent is just m equals to the m minus eta, the Greek symbol here, and then delt L over del M. So the derivative of loss in respect to M, which is the way that we're trying to train, right? So what I'm doing here is that I'm taking my derivative of loss right here, and I am saying, all right, okay, I am trying to take this, and then learning rate is just a constant of how much I change, and I'm trying to change in this direction. That makes sense, right?
Yeah.
So basically, if I have this rate of change, I will know how much to adjust my weight by. So first I will adjust over here. So now I get a real loss, another loss value, right? So because now my weight is over here.
Right. Yeah.
So now I can take the gradients again.
And it's the derivative is larger, like the higher the loss value.
Yeah, exactly. Right?
I see.
That's exactly what's going on here, right? So now my gradient will be smaller and then smaller, like all the way until I'm down here, right?
Right.
Where the gradients will be like really, really, really close to zero.
Yeah.
That's where I want to be.
Okay.
So this is what gradient descent is doing, and this is why we want to adjust the weight this way.
I see. Yeah.
Right? And therefore, because we are doing this, because we have this, eventually that I will change my m over here, and then finally I will come to a line that's the closest to my data that models my data. Now I have a good model.
Yeah.
Right? But what's important is to understand gradient descent and why we use the gradient descent as our weight adjusting algorithm. And that urges us to take the derivative of the loss function. And of course, for regression tasks like this, we're going to use MSE, but for yesterday's task, we're going to use cross entropy for classification tasks. But it's still the same concept, exact same.
So cross entropy is for classification, and then this is for like numerical data?
Yeah, this is for regression tasks.
Okay, regression.
Which involves with
Gotcha.
Numerical data, right?
Yeah, I gotcha.
But does this weight update policy make sense?
Yeah, no, it makes sense. I get it. Yeah. I get the general concept. I don't know if I could recreate it for you, but I get like the general idea. So
and that's what you need. Like you're not gonna need, well, at least for this class, you're not gonna need like to understand all the math, but you would want to understand why you're doing what you're doing.
Right.
That's gonna be important to you.
I see.
Right.
Okay. Yeah. Dang, man, you should be teaching the class. Sure.
I mean, what Dr. Xie is teaching has no problem. It's just the moment he's like just putting down the math formulas as if it just makes sense. Like that's not how it works, you know.
Yeah.
Because machine learning isn't pure math, it's very
Right.
application. So why do you use MSE, right? Why are you
Yeah.
taking the gradients of your loss function, and why are
Right.
you doing the descent? That's what's, difficult.
Yeah, that's kind of what I'm looking into, like what I kind of want to know and
Right.
grasp from it. So, yeah.
So I hope this makes sense.
Oh, yeah, thanks, man.
Yeah, and it's just and then the only difference between this and machine learning is that my M isn't M, right? It's a weight,
Oh, okay.
which
Yeah,
weight is like a whole matrix of weights of,
I see.
like, I don't know. So it's like on the it will have attribute amount of rows, and then how many like hidden layers you want, right?
Mm,
Or if you just want to like do a one layer, then it's just the output,
yeah,
the
I
output
see.
amount, right? So because then I know you haven't learned linear algebra, but then if you matrix multiply, this weight will turn everything into the y, and
Yeah,
that's a single layer neural network.